Thiessen.
Yeah, hi all. I'm Max or Maximilian. This is joint work with Georgy, Margarita, Fabio, and Francesco. Oh, oopsie. Okay, so you all probably know the online classification model. We have T rounds, a domain X labels Y. The adversary gives you a point. You have to predict the label for the point. And then afterwards, the adversary reveals the true point, and you get a mistake if you mispredict it, right? This is the classical model. The mistake bound is determined by the little stone dimension, we all know that. But there is also this nice variant of the online learning setup called self-directed learning, which is in some sense way nicer for the learner. The main difference is that in the first step, the learner itself picks the point. The rest is exactly the same. So you pick the point, you predict the label for the point, and then afterwards the adversary reveals the true label, and you again get a mistake if you mispredict it. And note that this is also different from active learning. In active learning, you would kind of count the number of rounds instead, and not the number of mistakes. Right, and in the binary case, this was the mistake bound was characterized like by the ranks of the game trees. Maybe you can imagine a bit how this would, like kind of like little stone trees, but a bit different. And yes, somehow there, in the last 2 years or so, there was like this novel regained interest in this setup. So like there was the SDDIM characterizing it in multi-class, and also the agnostic case was studied, and also more like regression and linear classification, and also like other variants, more like sequence transductive online models where like the whole sequence of instances is fixed in advance and given to the learner. So many varieties were studied. Okay, and I like to do graph stuff, so we looked at this problem on the graph, so node classification. Here you have the graph given, and the vertices are now your domain. So the nodes are the data points you want to classify. The edges somehow should represent similarity, and you want to learn this target labels blue, red, let's say. And actually this community here studied this a lot, like 15 years ago, let's say roughly 10, 15 years ago, like especially the active and online setting of this node classification problem was studied a lot. Right, and so we just thought, let's consider the self-directed node classification problem. And just to recap, now the learner picks a node, predicts a label for this node, and the adversary reveals the true label, and you get a mistake if you mispredict it. All right. So as you might already think, you need some assumptions on the labels. If you don't assume anything on the labels, you would just make a mistake all the time. And the assumption we make is the so-called geodesic convexity assumption. So let's say we already know that these two blue nodes, the dark blue ones, we already know their label. Then by the convexity assumption, we'll also know that all the labels on the shortest path between the two is also blue. So think maybe of the graph as a finite metric space, and maybe this makes then a bit more sense. So in Euclidean space, the set is convex if I can take 2 points, and then a line segment is contained in the set. On graphs, I don't have line segments, so I take shortest paths. And so this set would be, for example, this would be a convex set. And moreover, okay, one real-world example, this is like a collaboration network. And actually this dark green blue set is like almost convex. And it's really different from what you might expect from Euclidean space. It's more like this tree-like structure, but you can see like all the shortest paths are kind of inside. You never like really leave the set too much. All right, and our assumption for this talk, right, here is that both sets are convex. The blue and the red class is convex in the graph. And again, intuitively from the Euclidean space, we call this half spaces, right? In the Euclidean case, if you have two convex sets, they are separated by a half space. That's why we use the same terminology here. All right, so you could now think about applying like the usual tools and tricks. So why not, for example, try halving or something like that? So if you have a graph and you have like an arbitrary hypothesis space now on the graph, you get just immediately, for example, you can run halving, like ignore the self-directed aspect and just run an online halving algorithm to get this VC log n, and then you have this some basic lower bounds like VC over log n. So up to these two log factors, this is determined by VC here, loosely. And so in our case, VC dimension is actually quite interesting. It's this Hartwinger number is called, is determining the VC dimension, which is the largest clique minor of the graph. So maybe most of you maybe know like cliques in the graph, like fully connected parts of the graph. Clique minor is almost a clique, but you have these parts where you can have like paths in between. So if you would contract these paths, you would get the clique. And so this is kind of determining the VC dimension here, interestingly. And this is somehow a measure of sparsity of your graph. So somehow most real-world graphs have a very small Hartwinger number, this h of g. For example, planar graphs, you might have heard of this Kuratowski theorem or something like that. They have a Hartwinger number of 5. So yeah, and if you plug this in, we'll see that up to these log factors, our mistake bound would be like determined by this h of g. But unfortunately, enumerating these half spaces or just even deciding if there is single half space consistent with your data, so like the realizable ERM problem, is NP hard in our case. So you cannot really run halving or like all the optimal algorithms, you cannot really run them directly. So this is the focus of the work. What can we achieve in polynomial time? And we thought about what to do, and instead of looking like this big set of all these half spaces, and they're very complicated, we decided to look at a very simple local substructure, and this we call good quadruples, which are just these 4 nodes, A, B, C, D, with where you have like basically 2 crossing shortest paths. Why do we care about these crossing shortest paths? Is they kind of restrict your labeling by our assumption, because as soon as you know that these 2 are red or positive and this guy is blue, by the convexity assumption, this guy cannot be blue as well, because otherwise we would have like a violation of convexity in here. So as soon as you know these, this guy must be red as well. And then you can do some basic like counting graph theory arguments to see that actually the relative number of these good quadruples, so like overlapping shortest paths, is quite large for graphs where this Hartwinger number is small. So if this is a small number, then you have like a constant or like a constant fraction. Quite a lot of these kind of, this substructure appears often in your graph. All right, and so basically a rough sketch of the algorithm would be now find these ABC with positive, positive, negative, such that you have many corresponding nodes here, which you then get for free. So basically here you wouldn't make a mistake. And of course I skip some details, but basically we always, in each round, we find these 3 vertices, which allows us to get many labels for free, basically. And so our main theorem is the following. We show that there always exist nodes A, B, C, such that the number of these DIs is a constant fraction of the overall number of nodes. So basically in each round, we can learn a constant fraction of the remaining nodes. And then you can already maybe see where this is heading. Basically, as soon as you, let's say, get 1% of the nodes each time, each round, you get again this kind of halving behavior, because then we have like log 1 minus epsilon n rounds, which in our case ends up being like Hartwinger number to the 4 log n many rounds. And also correspondingly this many mistakes. So what are the takeaways? We kind of switch from like this perspective, let's do halving over like the majority vote over the version space. We instead do halving in this more local, like in the space of good quadruples. So I could imagine this also works, this idea, in many other situations as well, where you kind of forget the global structure, but like focus on the local things. And yeah, it's polynomial time, but we lose this factor from like VC Hartwinger number to Hartwinger number to the 4, unfortunately. All right, and maybe to finish, let me give you some quick intuition where the self-directed learning actually is powerful and helpful. So remember our goal is kind of to find these nodes A, B, C with like red label, blue label, and also ABC has to satisfy some property, so we get like many Ds here. And the way you can do this in self-directed learning is you kind of have this set of candidates for your node A. And then you just keep on selecting these nodes, and you predict the opposite label for A. So let's say, let's say you just ask a different node next to A or something, and you predict -1. If the adversary tells you it was a -1, you didn't make a mistake, so you don't care, right? So you can just continue predicting -1s for nodes because you will never suffer a mistake. As soon as you actually get a mistake, you will get a node which is actually positive. Okay? I hope this wasn't too confusing. So you can do this also like with B. You start querying nodes here. You say, okay, their label is -1. Their label is -1. And as soon as you get a mistake, you will actually get a node which is positive, as you wanted. And then the same with C. And I hope it was roughly clear that this wouldn't really work in online learning or active learning. Because in online learning, the adversary wouldn't just give you the nodes you need. It would just give you different nodes. While in active learning, you can kind of select the nodes you need, but then you don't have any control about their labels, right? The adversary would just give you the opposite labels or whatever. So this strategy, like of finding this particular substructure with these particular labels, this really works only under the self-directed model. Okay, so yeah, we have some more results on like multi-class learning on graphs. And also, interestingly, this can easily be transformed into like a noise-robust version. And we also studied a more common like case of homophilic clusters, so not like convex clusters, but like very dense, more classical case of node classification. And as future work, I would suggest people to maybe look at self-directed bandits, but I already heard some people might study this already. Yeah, thank you.
So how do you define homophilic clusters?
I mean, there are different ways, but in the end, you assume that, let's say, the inside of the clusters, you have many edges, but going from one cluster to the other, you have not many edges.
So low connectivity?
Yes, for example.
Low connectivity,
yes. And then you can correct, the mistake bound is not this Hartwiger number, but like, let's say the cut size, the number of edges or something like that.
Nice, okay. Any more questions? All right, great, let's thank the speaker again.